Hey everyone, it's Alice here from Top Mark Science, and today we will be looking at drag and friction. Throughout this video, we will be exploring how drag and friction interact with objects, examples of drag and friction in action, and experiments we can do to test drag and friction forces. Let's get started. Have you ever been walking along a path and wondered, why am I not slipping over? Maybe not, but you might be now. It's mostly to do with this category of forces called drag, which are forces that oppose motion, as a result slow objects down. Look at these three objects here. What is going to cause them to slow down? Well, a cyclist puts on their brakes, the air will slow down a football that has just been kicked, and eventually the ground it lands on. And this skydiver opens a parachute which relies on the air to slow it down. Without it, it would be a very fast landing. All of these examples require drag forces to slow them down, such as air resistance, water resistance, and friction. Air resistance occurs when gas particles bump into an object. Think about when you're running. You're running in this direction, and you feel the air hit you in the other direction. That is the air resistance slowing you down. It has big impacts on a wide variety of things, such as aerodynamics and design. Take these two modes of transport, for example. Which one would experience a greater force of air resistance when in motion? The bus. It has a greater surface area exposed to the air, thus experiencing greater drag in the form of air resistance, and as a result would struggle to get to the same speed as a race car. Water resistance acts in a similar way, only it's water bumping into an object rather than the air. In a similar way will impact how objects are designed and move in the water. Like this fish. Which one is more likely to experience greater water resistance? This one. It's taller and has greater area exposed by its fins, so more water can hit it and does not flow around the fish quite so easily, creating swirls of water called eddies and can make movement less aquadynamic. The fish will not be able to swim as fast as this one, which has a shape that favours the fluid flow of water around the fish, creating less eddies. Another force that causes things to slow down might be one that you've used when you are cold. Other than putting gloves on, what can you do to keep warm? We often rub our hands together, don't we? Rubbing them moves each hand in opposite directions, which generates friction. And this warms your hands up because friction will often lead to the release of thermal energy. Pause the video here to determine what direction the drag forces are acting on each of these objects. If you finish, try the challenge. Let's mark our work. Marking pens ready. So this car is pointing and moving in this direction. Therefore, drag, in this case air resistance, is acting in this direction. There will also be friction between the tyres and the road too. And the force diagram will look like this. Remember, we can place actual pictures with spots and or boxes. This duck is floating on water, moving in this direction. Therefore, there will be some air resistance acting against the duck, and also some water resistance between the base of the duck and the water. So we have a little more going on in our force diagram for this one. This fish is pointing upwards, so it's probably swimming to the surface of the body of water. So if it's swimming up, then water resistance is acting down against the fish, along with weight too. This skydiver is falling to the ground slowly with a parachute open. So the motion is down, and therefore air resistance is up, and the force diagram is shown here. And finally, this rocket is launching in an upwards fashion, and as long as it's within the Earth's atmosphere, it will experience air resistance against it. And the force diagram will look like this. Good job, everyone. Let's look at some more examples. The Earth then. It orbits the Sun, but why doesn't it slow down? Well, it's all to do with space being a vacuum. No, not that kind of vacuum. The vacuum of space means there is no air. No air means no air resistance. So the Earth can just keep orbiting the Sun every day, every month, every year, for billions of years. So what factors can affect friction then? Well, welcome to a little online investigation to see. On my table, I have a mass. I can use my Newton meter to pull the mass and measure the force required to do so. If I do it again, but now with a different surface under my mass, and again with another surface, I can compare how much force is required to pull the same mass on different surfaces, which will indicate how much friction there is. So before we get started, we'll need to check our knowledge on variables, which will help in a moment. We have our independent variables. The independent variable is the thing that I change in an experiment. It's the thing I am testing to see if it has an effect. The dependent is the thing I'm interested in, measuring. It is impacted by my independent variable. And finally, our control variable. The control is what we keep the same. Control, keep the same. This is to ensure factors I'm not interested in do not influence my results in any way. So based on what we've just gone through, pause the video here to plan out the experiment I demonstrated a moment ago, like the diagram on the right. For now, you will only need to be able to fill in the things I star next to them. If you finish, try the challenge. If you need to, replay the demonstration. Let's see what we've been able to fill in. If you have gaps, you can fill these in as we go through the answers. In this experiment, our independent variable is the surface because I am changing the surfaces from shiny table to sandpaper, etc. My dependent is the force, that I'm measuring the force required to pull the mass using a Newton meter. And my control will be the mass of the mass, because different masses will influence how much force is required to pull. This needs to stay the same. An example of a basic method could look like this. A method is a step by step. It's important that it's written in order that they'll happen and include key equipment that you might need. And a prediction. For example, I predict the carpet will result in a greater force to pull the mass. Let's investigate and take a look. Starting with my shiny table, I pull my mass and record 5 newtons of force. You can write this in your results table if you've copied it. Next, the sandpaper. I'm going to pull using my Newton meter and record 20 newtons of force. Change the surface to a rug, pull along, and record 12 newtons of force. And finally, the towel, which records slightly more with 15 newtons, but similar to a rug. Now that I have results in my results table, I can analyse my data to conclude that the sandpaper resulted in the greatest force, and definitely a greater force than a shiny table. This is because sandpaper is a rougher surface and therefore will generate more friction, and so requires more force to pull the mass along it. Pause the video here. This experiment is not quite perfect. How could we improve it to make our results more reliable? We would need to repeat our experiment to ensure we have done it at least 3 times for each surface, so we can calculate a mean and identify and remove anomalous results. These are results that do not fit the pattern and are probably caused by an error of some kind. For example, I could have pulled the Newton meter too hard suddenly, rather than a gentle, consistent pull, resulting in a higher force which is not accurate. Now a challenge task. Pause the video here and use the plan pyramid to plan an investigation for testing the effectiveness of an air resistance for a skydiver's parachute. Let's see how we got on. We may have some differences, but this is just an example. If I want to see how effective a parachute is, I want to see if small ones are better than large ones. So I will change the size of the parachute in my experiment. The effectiveness is determined by how long it took the diver to land after the parachute is deployed. If the size means they fall too quickly and hurt themselves, it's not effective. So I will measure the time that it takes to land after the parachute is released. And I'm going to keep the person diving the same so the force of weight remains consistent. My results table will look like this. My independent goes on the left and dependent on the right. And a basic method like so. Remember to keep it in a logical order and keep any key details like timing when you started it and stopped. And finally, my prediction, which also contains an explanation for my reason, using my knowledge that I've learned already. For example, I think the largest parachute would work best because it provides a greater area and therefore more air resistance would act to slow the skydiver down, taking the longest to land. So why is it that you don't fall over on regular ground, but maybe you do more on ice? Well, it's simple really. One has more friction and the other less. Time for our end of video quiz, guys. Are you ready? Question 1. True or false? Drag forces act in the same direction of motion. This is false. They act in the opposite direction of motion. Question 2. Name the missing drag force. Air resistance, friction, and water resistance. Question 3. Air resistance is the result of what colliding with an object? 2 words. Gas particles. Nice work. Question 4. Friction can result in the release of what store of energy? Thermal energy, or heat energy is also okay. And finally, what piece of equipment can we use to measure when investigating friction of surfaces? A Newton meter. Excellent work. Pause the video here before we finish to rate how you got on today. You can use this to see what you need to practice. Thank you so much for watching this video, guys. If you enjoyed this video and would like to see more from Top Mark Science, you can like this video and subscribe to this channel. I'll see you next time.